Okay, let's look at a scenario here now that includes some static friction. What we have here are stacked blocks, and the bottom block is attached to a cord running over a pulley, and then there's a third block that is attached at the end of the cord and hanging. What we're told is, I mean, the normal stuff about assumptions: the cord's massless and elastic, the pulleys massless and frictionless, and we are releasing the system from rest. What we're asked to determine is the minimum coefficient of static friction necessary that block two stays in place with respect to one while the system travels through some distance d. So, okay, there's a bunch there. The static friction that we're being asked about here, right? This static friction, this is going to be the static friction between the blocks there. So we're wanting to find the coefficient that is there between the blocks. What is the minimum coefficient necessary that the blocks stay in place together while the system is accelerating? And you can say, well, wait a minute. How do I know it's accelerating? Well, you were told that it released from rest and that it does travel through some distance d. So it was at rest and then it went into motion. That's acceleration, right? A change in velocity. Okay. We're also given the coefficient of kinetic friction. That is a given quantity, and that is kinetic friction. So there's sliding at the interface. That would be relevant to the interface between block one and the incline itself. We're given the angle of inclination and we're given all three masses. Good. So this is a nice problem. We're also this distance d here is given. So, that's kind of nicely laid out problem. Okay. Remember that we're using energy analysis here. Our overall approach is change in mechanical energy is equal to the works done by non-conservative forces, where work is defined as the scalar product between force and displacement. So we need both those things there. So that's what we want to analyze. We're interested in mu sub s. So I would say let's just start by looking at block two, right? I mean, you could start kind of anywhere, but I'm going to start in a place where I'm at least getting close to the thing that I'm being asked for in this problem. And they're asking me for the coefficient of static friction. I know that is going to act on block two, right? So I'll go ahead and start by analyzing that block. So let's start there. We have our free body diagram for block two. We're going to use a rotated coordinate system. And that'll help us find our works. I'm actually going to begin this analysis by looking at my energies. So my initial energy for block two, remember we're told the system is released from rest. So I don't have any kinetic energy. And block two is at the lowest point it will be in the interval that I'm studying. So I don't have any gravitational potential energy here. So actually, there's no mechanical, and there are no springs in the problem. There's no mechanical energy in block two initially. Now, final means after it has undergone this displacement d. What's block two doing? Well, it's now in motion, right? So I can say, all right, now it has some kinetic energy. And it's also higher than it started, right? It's also at a height that's higher than it started. So I can say, oh, all right. And then it actually has some elevation, M2G. And let me think about how much elevation it's gained here. Can draw a little right triangle for yourself. Here's phi. We know that the distance d is the displacement up the incline, and I'm interested in what is the change in elevation when the distance up the incline is equal to d. And I can know what that is. That's going to be d sine phi there, right? I can know here that my h is equal to d sine phi. So if it helps you, draw that little right triangle out for yourself. Depends on what you can see in your mind. So that's my initial and final just for block two here. And then what is the non-conservative work done on block two? Well, let's now pause and go ahead and go to the free body diagram for block two and see how we do there. And remember that we're using a rotated coordinate system here. So I'll have my normal force upward. I'm going to call that N sub two, normal force on block two. And then I know I'll have my weight, my one invisible force, and that's off axis by an angle phi that's given to us. Okay. And then remember that the only thing that's touching block two is the surface beneath it, and surfaces can exert normal forces and frictional forces. So we know this is where the force of static friction is acting. And once again, we want to figure out the direction. The direction of static frictional force can be tricky. But in a problem like this, I can ask myself, what direction is mass 2 accelerating in? What direction is mass 2 accelerating in? And I know it's accelerating in the same direction as displacement, right? It's accelerating up the incline. So there must be, what force is responsible for that acceleration? It's actually the force of static friction. The force of static friction is the force that's responsible for the block's acceleration up the incline. Yeah. You can ask yourself what would happen if that force of if the coefficient of static friction were zero between those two blocks, and that is that block two would go nowhere, right? Block one would slide out from underneath it, and then block two would like have its little roadrunner coyote moment, right? And then fall down. Okay. So that's the free body diagram for block two. I'm going to float my little displacement. I know my displacement, whoops, that wasn't great. My displacement is along the incline, upward, up the incline. It's along my x-axis there for my rotated coordinate system. Remember, we're rotating, so our coordinate system is rotated there. The work done by non-conservative forces on block two then, the only non-conservative forces here are normal force and friction. Normal force is at 90 degrees to displacement, so no work done by normal force. The only work there is going to be work done by friction, and that will be equal to the magnitude of my static friction times the magnitude of my displacement times the cosine of the angle between them. In this case, they're in the same direction. So if you had it in your mind that frictional forces always oppose displacements or always oppose velocities, that's not correct, right? Here's an exception to that. This is a case where static friction does positive work. So force of static friction, that's going to be my coefficient multiplied by my normal force. My normal force here is going to be m2g cosine phi. That should be getting pretty comfortable for you by now, multiplied by d. All right, so I've got that figured out. Now I can kind of put this together and see if I can maybe solve for my mu sub s and be done with this problem. Wouldn't that be sweet? So where I'm going here is final energy minus initial energy equals sum of the non-conservative works, right? So in this problem, that gives me 1 half m2v squared plus m2g d sine phi. That's my final energy minus my initial energy, which is 0, is equal to non-conservative works. And I have one non-conservative work and it's positive here. So mu sub s, that's the thing I want. So I'm so glad I have it on my paper. M2 G D cosine phi. All right. And then my job here is to solve for mu sub s. So a little bit of algebra there. When I solve for mu sub s, I'm going to get v squared over 2 GD cosine phi plus tangent phi. All right. So am I done? Am I done? Am I done? Well, no, because D is given, phi is given, but V is not given. Oh man. Okay. So we need to find that. In order to find that, though, hopefully I learned this from previous problems, is that maybe I can look at the entire system now. And if I look at the entire system, that, that can simplify my analysis somewhat. So now I'm going to take this situation and I'll apply energy analysis to the entire system. So what this tells us by looking at this is that we need to find that final speed there. We're not done at this point. So I'll look at entire system. So I'll say here, so now analyze entire system. Cool. So initially, let's look at the whole system. Where's my energy initially? Initially, and I guess I'm going to prime this first one here, and I'll have my second one, the whole system, be unprimed. Initially, the system's released from rest, and the two blocks, blocks 1 and 2, are at their lowest elevation. So I'm not considering any gravitational potential energy there. But block 3 is at its highest elevation. Aha. So I do have gravitational potential energy of block 3 initially. So that's going to be mass 3, G, D. Now, why is it D? Why isn't it H? Go back and look at the picture. Because block 3 descends a distance D, right? So initially, block 3 is a distance D higher than its final elevation. Cool. So that's my initial. And now I need to write my final energy. So in the final case, what I have is all three blocks are in motion, right? All three blocks are in motion. So I have kinetic energy of all three. I can write that this way. All three of my blocks are in motion, and the cord is inelastic, so they all have the same speed. Great, so I've got kinetic energy. Block 3 is at its lowest elevation at the end of the interval, so there's no gravitational potential energy there. But blocks 1 and 2 have gained this height h that we calculated when we were looking at the beginning of this problem here, right? So what that tells me is that I have, after the system has moved through D, blocks 1 and 2, so that's M1 and M2, have increased in elevation. How much? By a distance D sine phi. So this is a good place to pay attention, that when you have an incline and hanging mass situation, the height differences or elevation differences are not the same, right? The elevation differences are not the same. Okay, so keep an eye on that in future problems. I've got my initial, I've got my final, and now work done by non-conservative forces here. So we can go back and it's probably a good idea here to draw our free body diagrams for the other masses. So what we had here is a free body diagram for mass 2, but let's go ahead and do a free body diagram for mass 1, and then I'll do free body diagram for mass 3 here. For mass 3, fairly simple situation, right? Mass 1's a little bit more fun. But for mass 3, what do I have? I've got my tension upward and I have weight downward. That's my free body diagram for mass 3. So I have one non-conservative force, and that's tension there, right? And my displacement for mass 3 is downward. Okay. So there's that. We'll kind of leave that alone. And now we'll look at mass 1, because that's kind of fun to think about what are the forces on here. And this is a skill we need to have. So what's going on with mass 1? Well, again, we're using a rotated coordinate system, right? So if it helps you, you can kind of draw that on top of your physical diagram. We have tension. The string is attached to the block. What else is in contact with the block? Well, we have the surface beneath it that's in contact with it. That's exerting an upward normal force. So I can call that n sub 1. I don't care about the surface beneath it, so I'm just going to use one subscript there. The surface beneath it also is exerting a kinetic frictional force, right? Sliding up the incline. So there's an impeding kinetic frictional force there. to the left. Okay, so we've taken care of the surface beneath it and the string attached to it. Now we have to look at the other point of contact on block one, and that is that it's touching block two. So it's also being contacted on top, right? So again, that's a surface contact. Surfaces can do two things, normal forces and frictional forces. So there is going to be a normal force here that's normal to the surface. I'll call this N 1, 2, that's the normal force. Oh no, actually I called it N2 on the M2 diagram. So I'm going to stick with the same notation. N2, normal force there. And then, okay, Newton's third law time, you guys. There's also, if the static frictional force, that's a force at the interface between blocks 1 and 2, right? So let's keep an eye on our Newton's third law pairs. So here's N2 and there's N2. That's a third law pair. That's the normal force between the blocks at the interface between blocks 1 and 2. So guess what? Static frictional force happens at that exact same interface. So we need, that's also going to be part of a third law pair. What that tells me is that I have static frictional force plus kinetic frictional force. They're both leftward directed. Static frictional force is pointing to the right on block two. It must be equal and opposite on block one, so pointing to the left on block one. We've had this conversation in previous problems when we were doing force analysis applications. So it should be getting, I know this tends to stay kind of a little bit weird for students, but hopefully getting a little bit more comfortable. Okay, and then we're missing one thing, of course, and that is our one invisible force. We've done all the contact forces, right? If you think about it, you can have maximum two forces per surface. We have two surfaces, two forces per is four forces, the two normals and the two friction forces. We have the string attached, which gives us our one tension, and then we do have our one invisible force, which is the weight of the block. This is our internal angle there as phi. Okay, so block one is kind of like the money block here. There's a lot going on. And then it's useful to think about what is my direction of displacement with respect to the free body diagram so I can see what's going to really matter there. So when it comes to which forces are going to be doing work here, again, hopefully you've watched the previous videos and you can predict here that if I look at this as a system, tension's an internal force, so tension's net work on the system will be zero. So when it comes to work, what I really need to be looking at is the frictional forces here because tension's internal, it'll net zero. My normal force on block one is at 90 degrees to the displacement, so it's not going to contribute. My weight is a conservative force, so it's not going to contribute. Normal force two is at 90 degrees to displacement, so it's not going to contribute. So the only forces that are actually going to contribute system-wise to my non-conservative works are going to be these two frictional forces. So it's kind of nice. If you do a thoughtful um, analysis like this, then you are not having to go through all of the calculations to sort of figure out what ends up calculating and being equal to zero. So this tells me that what I have to care about here is I'm going to care about the works done by my frictional forces, right? Now, having said that, if I look at the force of static friction, I see that I have a third law force pair here. So static friction really for this system is an internal force, isn't it? It's not an external force, it's internal force. It's exerted by one block on the other. So if I were to consider force of static friction, it's doing positive work on block two, but it's doing an equal and opposite amount of work on block one. So similarly to the tension, if you were to calculate out, and feel free to do this if you want to see this, if you were to calculate out what the works by static friction are, those two works would sum to zero. Again, you'll get positive work done on mass two, negative work on mass one. So the only force that actually does negative work on the system is our force of kinetic friction. I thought that was, I know that was windy, but I thought it was worth spending time on, because otherwise you're like, why? Why is this the only one here? So that'll be force of kinetic friction, displacement, cosine 180 degrees here. And again, we're looking at, if you're wondering which free body diagram are we looking at, we're looking at the free body diagram for block one in order to figure this out. Okay. And okay, so the other kind of exciting thing here is I need to ask myself which normal force is going to go with this kinetic frictional force. So it's the normal force that's between block one and the surface. So, like here, if I go back to my physical diagram, I can know that N1 is the normal force between block one and the surface. So that's the normal force that I care about. So we can say that this is going to be um, mu k times N1 d and then -1. Okay. Now, normal force one. I'm going to go back to this free body diagram here and remember that this is one of the things that we are actually allowed to use second law for, and that is that I need to solve for normal force one here. So N1, you can apply Newton's second law along the vertical here. So I'm going to give myself a little space to do that here. So I can have, if I say upward positive, I can say N1 minus N2 minus M1 G cosine phi is equal to 0. Okay, so that allows me to express N1 is equal to N2 plus M1G cosine phi. Well, what's N2? We can go back to the free body diagram for M2 to figure that out. N2 is equal to M2G cosine phi. And we had already subbed that in when we did the analysis on that side. So N1 is equal to M2G cosine phi plus M1G cosine phi. So we can rewrite that as M1 plus M2G cosine phi. Okay. So now we can write out this work in a form that's a little bit more useful for us. So that'll be negative mu sub k, and then this is going to be m1 plus m2 g cosine phi. And that's multiplied by d. So I'm going to clean this up just a little bit here. Negative mu k g d, sum of the masses times cosine phi. Hopefully I got everybody in there that needed to be in there. Okay, so now I can write out my final expression here, which is of course E final minus E initial equals the sum of the non-conservative works. So let's do that. I have my 1/2. Now sum of my three masses here, speed squared plus M1 plus M2 G D sine phi minus energy initial, which is M3 G D, is equal to non-conservative works. For this problem, that's going to be negative mu k G D, sum of masses 1 and 2 times cosine phi. Awesome. Okay. And remember what we're after here, right? Yeah. So we are interested in So we want to solve for this expression. We want to solve for v, right? We want to get that speed, or it might even be that we just need to get v squared because we need to go back and sub it. Yeah, we just need to get v squared. We need to sub it in our expression for mu sub s there. So that's pretty sweet. We don't even have to take the square root of it. So we can just solve for v squared and sub it in there. Okay. Um, so I'm going to leave the rest of that to you, all the details and tons of algebra and other things that I want you to notice about the final expression are in the written solutions.